Good morning. So, we are going to get started on chapter 15, and this is kinetics. All right. So, in the last chapter, we learned about thermodynamics. We learned about whether a reaction is going to be spontaneous or not spontaneous. And that is very important to understand because when you have two things that you're going to have close together, you need to know whether they are going to react or not. Now, the second part of this is the kinetics of a reaction. So we can tell by calculating the delta G, or using the Gibbs free energy calculation, to see whether it's spontaneous, but that doesn't tell us the whole story. All right. So what we have to do is know the rate of the reaction as well to understand the nature of it. And I thought the book gave a great example of the importance that kinetics plays in reactions. It talked about the reaction of the combustion of ethanol, which we know, well, actually, I don't know if you know, but the burner that I use in class for as our Bunsen burner uses ethanol as the fuel, and so obviously it is something that burns very quickly. And so the combustion of ethanol would be ethanol plus oxygen creates, since it's complete combustion, then our products would be carbon dioxide and water. Well, that has a delta G of minus 1300 kilojoules. All right, so we remember from the last chapter that a delta G less than 0 means spontaneous. All right, so we have the combustion of ethanol has a delta G of negative 1300 kilojoules. All right, so it releases a lot of energy, releases a lot of heat, which is, in the form of a flame. But we have a second reaction, and everybody knows that rusting is a chemical reaction that happens to iron. So rusting happens, and when iron when it's oxidized, so when solid iron reacts with oxygen, it creates rust. Well, the delta G for this reaction, okay, is minus, it actually releases more energy than the combustion of ethanol. So if all we did was consider the delta G to see the impact of a reaction, we would say, well, rusting of iron actually creates more energy or releases more energy than the combustion of ethanol. But we all know that in real life, it takes a little while for rust to happen. So even though it releases more energy with the overall reaction, the rusting of iron obviously is a little bit different from the combustion of ethanol. And so when we study kinetics, this gives us the reason why delta G doesn't tell us the entire story. Okay, the delta G does tell us that it is spontaneous, it's going to happen. That's why, if you have anything metal, a car, any car that still has metal on it, a lot of them are made of plastic now, but anything that has metal, that over time it will rust. But with ethanol, it's not going to take a month for ethanol to burn. So we are going to study the rate of chemical reactions. All right. So I'm going to give myself more room to be able to do this. All right. So again, kinetics is just the study of the rate that a chemical reaction happens. Okay. And so the way that we calculate the rate is if we have a reaction A plus B reacts to produce C plus D, how do we calculate the rate that reaction happens? All right. So with this, the rate equals delta, which is the change, in concentration. So when you use the squared off parentheses, that denotes concentration, over the change in time. All right. Now, this equation, it's a general equation. The reason we have C in there, it doesn't have to specifically be C. It could be D. All right, it's the concentration of any of the products in this rate calculation. All right, so what that's saying is the change in the concentration of C over time. Now, if C is a product and the reaction is going towards the products, obviously, then C is going to be growing. Okay, the way that you calculate delta C is the same as anything. It's the final minus the initial. Okay, now if this is a product, then it's going to be growing, right? Because the initial should be 0. All we have are the reactants to begin with. And so the final is going to be greater than the initial, so this is going to be a positive number. Now, the rate can actually, if all you know, you're not going to know the concentration necessarily of the final product, right? You may just know the concentration of one of the reactants. You can use the same calculation, all right? But because it is a reactant, it's going to obviously be going down. You're going to start with a higher amount of A. As the reaction progresses, you're going to be using up A. So your A final will actually be smaller than your initial, so it's going to be negative. Well, to account for that, if you are using, so this is for products, for product concentration, all right? So if all you know is the reactant, then it would be a negative of the same equation, all right? So we have the reactant concentration. Now, the reason that we have this is the rate has to be positive, okay? And so because the rate has to be positive, if you know the reactant concentration, so if you know any of the initial ones, you can still do the same calculation. It just has to be multiplied by -1, because when you have the final minus initial, it's going to be negative. So if you multiply it by -1, then you're still going to get a positive rate. All right, still going to be per change in time. So that's a pretty simple equation. So let's do comp check number 1 that's on page 455. All right, so I hope you were able to write those down. Actually, they're the pink boxes on page 454, so it should be something that stands out to you anyway. So if we look at comp check number 1 on page 455, we are asked, okay, so in a study of kinetics, the concentration of one substance is measured to be 1.15 molar. Now, the concentration is always given in molarity in chemistry. So when you're talking about concentration for any of these, remember that our measurement for concentration in these is going to be molarity. All right, so the concentration of one substance is measured to be 1.15 molar at 0.00 seconds. All right, oh no, just 0.0 seconds. All right, and then it was at 15.0 seconds, so let's just do 15.0 seconds. The concentration was measured to be 0.98 molar. All right, so the first question is the substance a reactant or a product? This is important for us to know because if you remember, I showed you the 2 rate equations. And so it's going to be one if it's a product, it's going to be another if it's a reactant. So when we start out, we have 1.15 molar, and then after 15 seconds, we've dropped to 0.98 molar, then this is going to be a reactant because it is decreasing with time. Okay, it's being used up. So the rate equation that we will use is going to be the minus delta, let's just say A because we're going to go with that equation. We're just going to write out the generic equation first. All right, so our delta A is going to be our final. Okay, so we have 0.98 molar minus our initial 1.15 molar. Okay, That's going to be our A. Okay, and that's going to be our change in time is our final minus the initial, which obviously is going to be 15.0 seconds. All right, so when we subtract the top, we are left with, so we have minus, and we have minus 0.17 molar. Okay, and that is over 15.0 seconds. So when we have a multiply a minus times a minus, that equals a plus. Those change to plus. All right, and our answer is 0.011 molar per second. Okay, that's a lowercase s. I just made it big. Okay. Now, with our significant figures, because we're dividing here, we are looking at the number of significant figures. So we have 2 here, and we have 3 here. So our answer is going to be just 2 significant figures. Remember, with the decimal point, this 0 is not significant because there's not another number on the other side of the decimal point. So our answer for this would be 0.011 molar per second is our rate for this reaction. Now I would love to be able to do the experiment, and I don't know. I'm going to look at it. I may, if it's not going to be a 45-minute video, I may do that experiment just so you can see it happening. But for the most part, it shows us a concept that everybody's already very familiar with, all right? So if we look at the rate, so what things affect the rate of a reaction? Okay, there are a few things that are proportional to the rate, and it's stuff that we're already aware of. So when we talked about concentration before, okay, the reaction rate is going to increase as the concentration of the reactants increases. Okay, that makes sense. We did that before. We did it with the antacids, with the Tums in the vinegar and water. So the more vinegar that was in it, the faster it happened, the more it happened. So that makes sense. The reaction is going to happen faster with a higher concentration of the reactants. It also is going to be directly proportional. So that means it's directly proportional. When one goes up, the other goes up. The rate will also go up with the surface area. Okay, so as the surface area goes up. All right, and what surface area means is if, say, like if we used one of the Tums and we broke it up into little pieces, all right, and we put the same amount of Tums, we put one intact tablet in a glass of vinegar and one that was broken up. Well, the one that's broken up is going to be used up faster than the one that's intact because there's more surface area. There's more area for the vinegar to come in contact with. Another, I guess, kind of real life example of this is when I make fajitas or something, and I marinate the meat. What I like to do is, instead of marinating one big piece of meat and cooking it and then cutting it up, I like to cut it up and marinate it as little pieces, because then each little piece has more surface area to kind of absorb the marinade that I do. So the surface area, as it increases, the rate increases. All right, so those are 2 things, and those would have been illustrated by the experiment. And so again, if I decide that it's not going to take too much time, I may do it and see, and I may post a video of doing that experiment. But for right now, we're just going to stick with the theory and move forward with that. So I'm going to close this video, and we will move on to the collision theory in the next one.